let's investigate these fates of pyruvate on our big picture view of glycolysis. We'll go ahead and talk first about the further oxidation fate, right, whereby pyruvate is going to enter into the mitochondrial matrix, assuming that this is a eukaryotic cell, and then from there pyruvate is going to get converted into acetyl-CoA, and then it's going to head to the top of the TCA cycle, where that TCA cycle will turn, further oxidizing the molecules and leading to the formation of more reducing power and more ATP. So this is the TCA cycle in there. So that's fate number one, further oxidation, and we're going to be looking at the details of that very shortly. However, fate number two, right, well, a couple that we talked about in between, right, but let's talk now about fermentation. What happens when there is no electron transport chain, or perhaps there is not a functional electron transport chain, or there is no terminal acceptor for this electron transport chain, which spans the inner mitochondrial membrane. So what happens then at that point is that the TCA cycle cannot run. Right? The ETC cannot run. The transition step cannot occur. None of the stuff that occurs in the mitochondrial matrix is pertinent anymore. So under conditions of fermentation, we might as well just ignore that stuff, and in fact I'm going to erase it to let us know that that can't happen under cases where there is no electron acceptor, or where that electron acceptor has run out, or where there is no ETC at all. So we'll just get rid of that, and then we'll have the possibility of pyruvate being the electron acceptor in fermentation. So when that is the case, then pyruvate is one of two kinds of fermentation. Pyruvate is either converted to acetaldehyde, if we say this is a yeast cell, and then it is converted to ethanol, right? Yeah, alcoholic fermentation, right? Okay, so that is one potential if this is a yeast cell. And the purpose of that, the whole purpose of pyruvate getting turned into ethanol, is to allow this reducing power produced right here in glycolysis to get regenerated, because that NADH has nowhere to carry its electrons because there is no ETC, or it's stopped running, or it's no longer got an electron acceptor, so that NADH has nowhere to go. So in order to keep step 6 of glycolysis running, pyruvate is converted to ethanol, and that conversion, which we recognize as being the backwards reaction by which your liver detoxifies alcohol, will use up this NADH. So the NADH will come over here, drop off its electrons, become itself oxidized, and go back right here to this step 6 and keep this step 6 running. So it'll be re-reduced, NAD plus back to NADH, right there, keeping step 6 going. Now that's the purpose of alcoholic fermentation in a yeast cell. Much to our dismay, it's not to produce the alcohol that we like. In fact, it's to keep glycolysis running so that a yeast cell can keep on making ATP in step 7 and step 10 to get a net of 2 ATP. Right? So a fermenting yeast cell can produce 2 ATP with alcoholic fermentation. Okay, awesome. Now, there is another type of fermentation, right? If we're looking at the muscle cell, one of our muscle cells, it's not going to be doing ethanol or alcohol fermentation. It's not going to be producing ethanol. Instead, we know that it's going to produce the byproduct lactic acid, and lactic acid will be a product of fermentation. So let's look at the situation there. It's the same idea, except for that instead of pyruvate getting turned into ethanol, pyruvate is now going to get converted to lactate. And in that process of forming a lactate, NADH is again going to drop its electrons, become oxidized, and keep step 6 of glycolysis moving and running and going so that the cell can continue to net ATP to ATP via glycolysis. So that's the purpose of fermentation. Let's talk now individually about each type of fermentation, alcoholic and then lactic acid. So here are the details then of alcoholic fermentation, very much the same as what we just drew on our big picture view, only here we're looking a little bit more at structures. So if you will, this is the down and dirty glycolysis right here, glucose becoming 2 pyruvates with the yield of 2 ATP and 2 NADHs. So that's the short version there. But we know then in alcoholic fermentation that pyruvate is converted first to acetaldehyde, and notice that what that allows, or what occurs there's a loss of a thoroughly worn out, all used up CO2 in this process. And in fact, this is a large reason why as our wine is brewing, we're going to watch it bubble, and in fact at times it may get pretty rampant with bubbles of the CO2 produced in this particular step. So that is made possible by the enzyme pyruvate decarboxylase, so this decarboxylation reaction. And so then acetaldehyde formed, and we can see there a very familiar sort of aldehyde structure. Acetaldehyde then now is what serves actually to regenerate the NAD plus produced in glycolysis and keep glycolysis going. So that NADH drops off its electrons. They're not worth anything right now. They can't be used as currency for energy because the ETC is not running. So they dump their electrons off right here and just simply get regenerated. It's like nobody wants pizza right now. It's not worth anything. So it's just getting recycled for its parts, if you will. And it's forming a toxic byproduct even in that process. Alcohol dehydrogenase, of course, then forming ethanol. Now notice, this is the enzyme that we know and love and have met before, because in our liver it can catalyze the reverse reaction of ethanol getting detoxified back to acetaldehyde and to pyruvate. So we like the reverse reaction, which actually generates reducing power. We'll talk more about that even as we go, always more about alcohol dehydrogenase. Okay, now let's look then at lactic acid fermentation, the other kind of fermentation where acetaldehyde is not formed, but instead pyruvate is converted directly to lactate. So this is a kind of anaerobic metabolism that would occur within our muscles under situations where oxygen is not prevalent enough to keep the ETC running. So here we see it happening, the same down and dirty version of glycolysis, converting to 2 pyruvates and forming 2 ATPs and 2 NADHs. And this time the pyruvate itself directly acts as the receptacle for those unneeded, unusable electrons from NADH and is converted to lactate in that process. The enzyme that does this is lactate dehydrogenase. We've talked about a bit before. And now lactate dehydrogenase is also a pretty cool enzyme in that some forms of it can convert lactate backwards into pyruvate. Okay, so let's think about this in terms of why this might be a sort of interesting thing to a lot of us. Just the other night I was running a 5K race, and as I was running I was picturing my electron transport chain running out of oxygen, not having enough oxygen to suit all of my energy needs that way. And so as I pushed up the hill I felt the burn of anaerobic metabolism and recognized that lactic acid was accumulating in my muscle tissue. And so I started to just get pretty excited cheering for the lactate dehydrogenase enzyme that exists not in my muscle tissues, right? Because in muscle tissues this lactate was accumulating, but in my heart and in my liver, the enzyme that can catalyze the reverse reaction, converting lactate backwards to pyruvate, and in the case of the heart, using that pyruvate as an energy source, or in the case of the liver, converting that pyruvate backwards into glucose, which it can then ship back off to my burning muscles. So I was cheering for lactate dehydrogenase in both my liver and in my heart and saying, yes, convert more of my lactic acid from my muscle tissues backwards into pyruvate and then backwards into glucose in the case of the liver, to power my burning muscles again and ship that glucose back off to my burning muscles. So depending upon the tissues, there are different forms of lactate dehydrogenase, and we could say that in all the tissues, the lactate is the byproduct of anaerobic metabolism, but some of those tissues have the capability to catalyze the reverse reaction, helping to clear that lactic acid from the tissues, in the muscle tissues in which it is accumulating. Remember that with any tissue, when that tissue can no longer meet the needs of energy production using aerobic respiration alone, that is, you can't get enough oxygen to your burning tissues in order to get ATP from the electron transport chain, the TCA cycle, and you just can't get enough that way, then that's when lactic acid starts to accumulate, because of the fact that you need more ATP than your body can provide using aerobic respiration. So if you will, then L-lactate is the byproduct of anaerobic metabolism produced by all tissues when oxygen supply is inadequate.
Hey guys, I'm not gonna lie, I'm super pumped about this. Here we are again in my kitchen, and we are here to talk about the fates of pyruvate. Yes, the fates of pyruvate in the kitchen. Sounds kind of kinky, but here we have it. A few days ago, what I did was I took some white grape juice and some water, and it was white grape juice concentrate, and I boiled it. And I also took I had a huge bag of really fresh plums, and I peeled them and I ground them in the Cuisinart, and I made, plum puree, and I mixed the juice of one lemon with the grape juice, the boiled grape juice, and I poured it over the plums. And for the last few days, I've had a mixture of that just covered by this cloth in a ceramic container, and I've been stirring it twice a day. So come a little closer, and I want to show you what these yeast look like right now. So I added wine yeast to this, and the wine yeast have been growing in here, and twice a day I've been stirring this. So note that the yeast right now are growing aerobically. They're growing aerobically, and so what's the fate of pyruvate? I hope you said it. Further oxidation, right? So now pyruvate is headed into the mitochondrial matrix of the yeast cells, where it is being converted to acetyl-CoA, where then it can add into the TCA cycle, right? So it's being further oxidized. However, our goal here today is to change the fate of pyruvate. We're actually going to take this aerobically growing mixture of yeast, which, man, look at them grow, and we're going to starve them of oxygen. Sounds kind of mean, huh? And it really is, because we're going to change the fate of pyruvate, right? We're going to change the fate of pyruvate so that now pyruvate is going to be converted to acetaldehyde, and it's going to be the electron acceptor in fermentation. So we're going to ferment, we're going to make some booze. All right, let's go ahead and see what we can do now. I have here a couple of, I have toys. Toys are fun. And one thing I've got here is a funnel that has a strainer in it. So we're going to strain out some of the bigger chunks in here, and you're going to see whether or not I have good pouring skills as we pour this into a large jar. And I've also got a cute little toy here. We're going to fill this up with water to the fill lines on it. I don't know if you can see that there. And I want to come a little closer and see, okay, see these fill lines on there? We're going to put water in there until basically what we're doing is forming a U-tube full of water. So what that will allow is it will allow the gas to bubble out of here, but it won't allow any gas to enter, right? So no oxygen can get in, but all that thoroughly worn out, fully used up, totally oxidized carbon in the form of CO2 can just bubble right out of there. Pretty sweet, huh? So, hey, by the way, CO2 is formed, right? Whenever pyruvate is converted to acetaldehyde, one thoroughly worn out, fully used up CO2 is lost, right, out of there. So it's just going to bubble, man, and it's going to bubble like mad. Maybe we'll visit it a little bit later. You can already see how madly it's bubbling here. Okay, let's see how well I can do. I'm going to give this one more quick stir. We'll see if we can siphon out some of the larger particulate matter in here.
You're missing.
It's going to take a while. We may have to go to time lapse.
It's not really going
it's not
down.
really even going to go through. That took a while, so we had to do it cooking show style, and that's cool. Oh, and I remembered one thing I forgot to tell you. After boiling the water and the juice, I added 6 cups of sugar to that. Why? Because, well, glucose is the starting metabolite for glycolysis, right? And so it's important that we added enough of that to start out glycolysis and get it kicking and running. All right, here we are. We're ready to put in the stopper and starve the yeast of oxygen. So they will now convert. The fate of pyruvate will change. It will go from being further oxidation to being fermentation. And of course, pyruvate will get converted now to acetaldehyde, which acetaldehyde will serve as the acceptor of electrons for NADH, and so everything will keep on running, and glycolysis will be the only thing that powers the yeast now. So I sometimes joke that after I do this step that the yeast turn around and give me the finger, because they went from being able to make all kinds of energy. In fact, we're going to see coming up about 30 to 32 ATPs they could make from one glucose molecule before I stuck the stopper in there. Now that I stuck the stopper in there, they can only make 2. Yeah, you can see why I get the finger for that. Check this out, you guys. It's only been like 2 minutes, and look at it, it's already bubbling like mad. This is going to be some good stuff.